Why did humans start walking on two legs? What real evidence tells us? When we talk about humans, we most often think of intelligence, speech, culture, technology, art, and the ability to build cities. But if we look at ourselves through the eyes of an evolutionary biologist, one of the most important human traits becomes visible much earlier. We walk on two legs. We do not simply stand upright from time to time like a bear, an ape, or a meerkat. Instead, we made bipedalism our main way of moving. Our body is built around this habit: the pelvis, spine, knees, feet, head position, gluteal muscles, and even the mechanics of childbirth are connected to the fact that we became two-legged beings. The main question sounds simple: why did this happen? Why did the evolutionary line that led to humans move away from the four-limbed locomotion typical of many primates and gradually shift toward walking on two legs? For a long time, there was a simple popular answer: our ancestors left the forest for the savanna, the grass became tall, and they had to stand upright to see over it. This image is easy to understand, but modern science shows that reality was more complicated. Bipedalism did not appear in a single moment, was not the result of one single cause, and was not an instant transition from an ape in the trees to a human on the plains. Real evidence points to a gradual mosaic. Ancient hominins still climbed trees, but could already walk on two legs. They lived not only in open savannas, but in changing landscapes with forests, shrubs, bodies of water, and open areas, and bipedalism provided several advantages at once: energy efficiency, free hands, easier carrying of food and infants, access to food, better thermoregulation, and more efficient movement between resources. To understand why humans began walking on two legs, we must first separate evidence from beautiful myths. Bipedalism appeared before a large brain. One of the most important conclusions of paleoanthropology is this: our ancestors began walking on two legs before their brains became much larger. This is crucial. In the past, one could imagine that first there appeared an intelligent human who began making tools, hunting, speaking, and only then started walking upright. Fossil discoveries show the opposite. Bipedalism was one of the earliest human traits. Lucy, the famous skeleton of Australopithecus afarensis, lived about 3-2 million years ago. Her brain was much closer in size to the brains of modern great apes than to that of a modern human. But the structure of her pelvis, femur, and knee joint shows that she already moved on two legs. This means that bipedalism was not a consequence of a large brain. Rather, it became one of the basic platforms on which other human characteristics later developed. The even older Ardipithecus ramidus, which lived about 4 million years ago, also shows a mosaic picture. It was not like a modern human, nor like a modern chimpanzee. It retained traits related to tree climbing, but at the same time had features associated with moving on two legs. Its big toe could still move to the side, helping it grasp branches, but the pelvis and some elements of the skeleton indicate an ability to walk upright. There are also even older candidates such as Sahelanthropus chadensis, which lived about 6-7 million years ago. It remains the subject of much debate because the material is limited and the bones are fragmentary. But some studies suggest that its femur may have had signs of habitual bipedal movement, while its arms retained adaptations for climbing. Even if some interpretations are later refined, the overall picture is already clear: bipedalism arose very early, long before the appearance of modern humans. What evidence do we have? The main evidence for bipedalism falls into two categories: bones and footprints. Bones tell us how the body was built. In a bipedal creature, the head must balance on the spine differently than in a quadruped. That is why scientists examine the position of the foramen magnum, the opening where the spinal cord connects to the brain. In animals that walk on four limbs, the head is usually positioned forward. In bipeds, it is better balanced above the spine. The pelvis is also important. In modern humans, the pelvis is short, wide, and bowel-shaped. It helps support the internal organs, stabilize the torso, and transfer weight from one leg to the other during walking. The chimpanzee pelvis is different, it is more elongated and adapted to another type of movement. In early hominins, the pelvis was not fully human, but its changes show movement toward a bipedal gait. The femur is important as well. In humans, the thigh bone angles inward toward the knee. This helps place the feet closer to the body's center of gravity. Thanks to this, we do not sway too strongly from side to side with every step. The knee joint, ankle, and foot also carry traces of bipedalism. The human foot became a supporting platform, the big toe is aligned with the others, the arches of the foot work like a spring and lever, and the heel absorbs strong impact during walking. The second type of evidence is footprints. They are especially valuable because they are not just bones that require interpretation, but direct evidence of movement. The most famous example is the Laetoli footprints in Tanzania, dating to about 366 million years ago. Several ancient beings walked across wet volcanic ash, which later hardened and preserved their steps. These footprints show bipedal walking long before the emergence of the genus Homo. Most likely, they were left by representatives of Australopithecus afarensis, or closely related hominins. The Laetoli footprints are important also because they show not merely the ability to stand on two legs, but regular locomotion. The prints have direction, sequence, depth, heel shape, and forefoot impressions. From them, scientists can judge weight transfer and the nature of the stride. They are among the strongest pieces of evidence that bipedalism was already a stable part of early hominin behavior. Why the idea that they simply left for the savanna is too simple. The popular savanna hypothesis sounds logical. Forests disappeared, human ancestors found themselves on open plains, they needed to see predators, carry food, and walk long distances, so they stood up on two legs. This version contains rational elements, but it does not explain everything. First, the earliest hominins with signs of bipedalism did not necessarily live in a completely open savanna. For example, the remains of Ardipithecus ramidus are associated with a forested or mosaic environment. There were trees, shrubs, and areas of more open terrain. This breaks down the simple picture. First the forest disappeared, then bipedalism appeared. More likely, bipedalism began to form in an environment where trees still played an important role. Second, the earliest bipedal hominins were not walkers like modern humans. Many retained long arms, curved fingers, grasping abilities in the foot, or other signs of climbing. This means evolution did not follow the scheme yesterday in the trees, today in the savanna. For a long time, our ancestors combined different ways of moving. They climbed, clambered, walked on two legs, and perhaps sometimes used their hands for support. Third, the savanna itself is not a uniform sea of grass. African landscapes changed. The climate fluctuated, forests retreated and returned, rivers created corridors of vegetation, and open areas alternated with shrublands. In such an environment, versatility could be more important than narrow specialization. An animal that could both climb and walk on the ground gained an advantage. That is why the modern answer is more cautious. Bipedalism probably did not arise because of one great cause, but because of a set of advantages that strengthened one another at different times. Version 1: Energy efficiency. One of the most convincing reasons is energy efficiency. For modern humans, walking on two legs is very economical. We can walk for a long time while spending relatively little energy per unit of distance. Experiments comparing human and chimpanzee walking have shown that human bipedal walking is significantly more efficient than typical chimpanzee locomotion. This does not mean that ancient Australopithecines immediately walked as efficiently as we do. But the direction of selection is clear. If an individual could cover more distance using less energy, it had an advantage. Why does this matter? Imagine a mosaic landscape. Food is unevenly distributed. Today fruit is in one place, tomorrow in another. One needs to move between trees, shrubs, water sources, and open areas. If the distance between resources increases, energy savings begin to matter. Even a small advantage repeated every day over thousands of generations can become fixed by natural selection. Four-limbed locomotion is efficient for many animals, but for an ape with certain body proportions, the transition to regular ground movement may have been energetically costly. Knuckle walking, as chimpanzees and gorillas do, is not the universal original state of all great apes, but their own specialization. Our ancestors may have taken a different path, not toward improved knuckle walking, but toward increasingly stable bipedalism. The energy hypothesis does not explain everything, but it works well as one factor. Bipedalism may have been advantageous not because it immediately made human ancestors fast, but because it made them more economical walkers. Version 2: Free hands. The most obvious consequence of bipedalism is the freeing of the hands. When the forelimbs are no longer needed for constant support, they can be used for many things. Carrying food, holding an infant, carrying a stick, gathering fruit, pulling down branches, transporting stones, defending oneself, or building simple shelters. It is important not to confuse cause and consequence. We cannot say that humans began walking upright because they were already making complex stone tools. The earliest signs of bipedalism are older than most reliable evidence of developed toolmaking. But the freeing of the hands could have become a powerful bonus that reinforced and strengthened bipedalism. An ancestor that could walk some distance with food in its hands could bring resources to a safer place or share them with a partner and offspring. This could affect offspring survival. If a female could more effectively carry an infant or food, that was also an advantage. If a male or a group could transport valuable food from a place of acquisition to a resting place, social life change. There is a provisioning hypothesis according to which carrying food and providing for a partner or offspring played an important role in reinforcing bipedalism. It has controversial elements, especially when it tries to reconstruct the family relations of ancient hominins in too much detail. But the idea of carrying as an advantage looks realistic. Free hands are too important a consequence of bipedalism to ignore. Version 3: Feeding and posture during food acquisition. Bipedalism may have begun not with long journeys across the ground, but with short episodes of standing and balancing while obtaining food. Modern great apes sometimes stand on two legs when reaching for fruit, holding branches, moving across flexible branches, or manipulating food. If ancient ancestors often adopted a vertical posture in trees or near low branches, natural selection could gradually strengthen anatomical traits useful for such a posture. This version is called the postural feeding hypothesis. Its meaning is that bipedalism may have grown out of behavior related to feeding, standing up, reaching, maintaining balance, and freeing the hands for gathering. At first, it was not a fully human gait. It consisted of episodes, a few seconds, a few steps, moving from branch to branch, gathering fruit. But evolution often works exactly this way. A new function emerges from old behavior. This hypothesis fits well with evidence from early hominins that retained arboreal adaptations. If the first bipedal beings still climbed a great deal, it is logical to search for the origins of bipedalism not only on the ground, but also in the trees. Perhaps bipedalism was first a way to use the hands better while feeding, and only later became the main method of movement on the ground. Version 4: Thermoregulation. On two legs, the body receives less direct solar radiation at midday than it does on four. A vertical posture reduces the surface area facing the sun and raises the body above the hot ground, where the air may be cooler and wind movement stronger. This could have helped with cooling in a hot open environment. The thermoregulation hypothesis is especially interesting if we imagine not a fully forested environment, but a mosaic landscape. Part of the time, ancestors were in open areas where overheating was a real threat. A more vertical posture could reduce heat load and decrease the need for water. For an animal living in a hot climate, that is a serious advantage. However, this version has a limitation: it was probably not the first cause of bipedalism. If the earliest bipedal hominins lived in forested or mixed environments, cooling on the open savanna cannot fully explain the beginning of the process. But thermoregulation may have become an important factor later, when some hominins began spending more time on the ground and in open habitats. Version 5: Safety and better visibility. Another popular idea is that by standing on two legs, human ancestors could see farther, noticing predators, competitors, or food resources. This makes sense, but as a main cause, this hypothesis is weaker. Constant bipedalism requires major anatomical changes. If an animal only needs to look around occasionally, it is enough to stand briefly, as many animals do. For that, there is no need to restructure the pelvis, foot, spine, and knees. Moreover, a vertical posture makes an animal more visible not only to itself, but also to predators. Therefore, better visibility may have been an additional advantage, but it is unlikely to be the only explanation. It looks far more convincing when combined with other factors. If a hominin was already often walking on two legs for food, carrying, and energy efficiency, better visibility became one more benefit. Why there was not one cause, but a whole complex. In evolution, it is rare for one factor to fully explain a major change in the body. Bipedalism affected almost the entire skeleton. It brought advantages, but also created problems. Humans developed back pain, difficult childbirth, risks of knee and foot injuries, and heavy load on the spine. Therefore, the benefits must have been strong enough to outweigh the costs. Most likely, the process looked like this. The common ancestor of humans and chimpanzees already had abilities related to vertical postures, climbing, balancing, and using the hands. Under certain conditions, these abilities became more useful. It was necessary to reach food, stand on branches, carry objects, and move between forest patches and open terrain. Individuals whose bodies coped slightly better with vertical posture and walking on two legs gained a small advantage. Then the environment changed. The climate became more variable, forests became fragmented, and resources were distributed in patches. Bipedalism became useful not only in trees or near them, but also on the ground. It allowed energy savings during movement, made it easier to carry food, helped with cooling, and freed the hands. Gradually, natural selection fixed changes in the pelvis, femur, knee, foot, and spine. At the same time, different hominin lineages may have experimented with different forms of bipedalism. There was no single straight ladder, ape, Australopithecus, and human. There was a bush of evolutionary branches. Some species climbed more, others walked better, and still others combined both methods. Some disappeared, while others gave rise to new forms. Humans are not the result of a perfect plan, but of a long series of compromises. The Laetoli footprints, the moment theory became an imprint. The Laetoli footprints are among the most emotionally powerful pieces of evidence in the science of human origins. Bones require imagination. One has to reconstruct muscles, gait, and movement. But footprints are the movement itself, frozen in time. Several beings walked across wet ash almost 3.7 million years ago. They did not know they were leaving a message for the future. Yet those prints became direct evidence that long before us, bipedal ancestors were already walking across the earth. Everything in these footprints matters: the direction of movement, the sequence of steps, the heel impression, the transfer of weight toward the front of the foot, and the absence of hand support marks. They show that bipedalism was not an accidental posture. It was a way of moving. Laetoli also reminds us that walking on two legs began with beings that were not yet human in the modern sense. They did not have our culture, cities, writing, or science. Their brains were small. But they had already made one of the most important steps in human evolution, literally a step. Lucy, a small brain, but an upright step. Lucy became a symbol because her skeleton showed a combination that once seemed surprising to many: a small brain and a bipedal gait. This was a blow to the old idea that humans first became intelligent and only then stood upright. Lucy was short, light, and had traits reminiscent of an arboreal past. But her pelvis and legs said she walked upright. Of course, Lucy did not walk exactly like a modern human. Her gait may have differed, and her body retained abilities for climbing. But this does not make her less important. On the contrary, Lucy's mosaic nature shows real evolution. New traits do not appear all at once. Some parts of the body change, while others remain ancient. Bipedalism developed not as an instant transformation, but as a gradual restructuring. Ardipithecus bipedalism was not necessarily born in the open savanna. Ardipithecus ramidus is especially important because it is more than 1 million years older than Lucy and shows an even earlier stage. Its remains are associated with a forested environment where there were trees and animals typical of closed or mixed habitats. This is a serious argument against the overly simple savanna version. Ardipithecus had an unusual combination of traits. It could move on 2 legs on the ground, but its foot retained a grasping big toe. It climbed, but it was not an exact copy of a chimpanzee. This points to an important fact: modern chimpanzees are not living human ancestors. They too have gone through their own evolution. Our common ancestor was probably not fully like either us or them. Therefore, the question "why did we stop walking like chimpanzees?" is not entirely accurate. It is possible that our lineage never passed through a stage of full chimpanzee-like knuckle walking. Humans and chimpanzees may have inherited different behavioral elements from a common ancestor and developed them in different directions. The cost of bipedalism. To understand why bipedalism became fixed, we must remember its cost. The human lower back is vulnerable. The knees bear heavy loads. The foot can deform. Childbirth in humans is more difficult than in many other mammals because the pelvis must both assist walking and allow the passage of a baby with a large head. Bipedalism is not a perfect engineering design. It is a compromise, but evolution does not create perfection. It preserves what works well enough and provides an advantage under specific conditions. If bipedalism allowed energy savings, made it possible to carry food, freed the hands, helped obtain more resources, and supported survival in a hot mosaic environment, then its benefits could outweigh its cost. This is why the human body looks like a set of compromises. We are not the fastest runners among animals, not the best climbers, and not the strongest. But we are very good walkers. We can walk for a long time, carry objects, keep our hands free, cool ourselves through sweating, plan a route, and return with resources. For our ancestors, this may have been more important than instant speed. What can be considered the most likely answer? The most honest scientific answer is this: humans began walking on 2 legs not for one single reason. Bipedalism arose gradually among ancient hominins who still retained a connection with trees but increasingly used the ground. At first, vertical posture may have helped with feeding and movement in a complex tree and ground environment. Later, bipedalism became advantageous when moving between resources, carrying food and infants using the hands, and living in more open areas. Still later, advantages related to cooling, long-distance movement, and social cooperation were added. If we reduce everything to one sentence, it would be this: humans became bipedal because, in a changing environment, 2 legs freed the hands, saved energy, and gave our ancestors a new way to live between trees and open ground. But it is important to add, this was not a goal. Evolution did not plan humans. No one chose bipedalism for the sake of future cities, writing systems, or spacecraft. Small anatomical advantages accumulated generation after generation. Those who walked slightly better, carried food slightly farther, cooled slightly more effectively, and cared for offspring slightly more successfully left more descendants. Over millions of years, these slightly better traits turned into a fundamental feature of our species. Why this question matters today. The history of bipedalism is the story of how humans began not with the brain, but with the body. Before language, religion, mathematics, and technology, there was a step. Before stone cities, there was a footprint in volcanic ash. Before philosophy, there was a restructured pelvis, knee, foot, and spine. This makes human origins both more earthly and more astonishing at the same time. We are used to thinking of ourselves as beings of reason. But reason emerged inside a body that spent millions of years learning to move differently. By freeing the hands, bipedalism opened the path to manipulating objects. Economical walking expanded the space of life. Carrying food and caring for offspring may have strengthened social bonds. A new posture changed relationships with the landscape, predators, food, and one another. That is why the question, why did humans begin walking on two legs, is actually broader. It is about how a small behavioral change can restructure an entire evolutionary trajectory. To stand on two legs means to see the world differently, move differently, use the hands differently, and distribute energy differently. It was not just a way of walking. It was a new biological strategy, and the most real evidence for this strategy lies not in legends, but in bones and footprints. In Lucy's pelvis, in the Laetoli footprints, in Ardi's mosaic skeleton, in the disputed ancient bones of Sahelanthropus, in comparisons of human and chimpanzee walking, and in the shape of the human foot and pelvis. All of them say the same thing: bipedalism was an early, complex, and gradual process. It did not make us human instantly, but without it humans in the modern sense most likely would not exist.